Okay, this is a short, just a brief note about non-dimensional numbers and their importance and what we'll be studying in this class. One place that non-dimensional numbers arise is from the governing equations. If we look at the terms of the equations and rescale them, we can see we can get a sense of their importance for different flow fields. And so that's what I'd like to do first, is just have a look at that. If we take the momentum equation, this will be the x momentum equation. Let me just write this out quickly. I'll write this in Einstein convention form. So this term that I'm writing right here is actually three terms, where the index, repeated index, is repeated over all three indices, I, j, and k, or 1, 2, and 3, or x, y, and z. Negative 1 over rho, partial p, partial x, plus, and I'll just keep a constant kinematic viscosity, so I'll pull it out of the second derivative here. Okay, so this is repeated over three terms and three terms as well, but they all look pretty much the same, and it won't affect the scaling. So this is the x momentum equation, and what I'm going to do is non-dimensionalize it. So if we take each of these variables, essentially you have velocities, u, v, and w components, the three components of velocities. We have density, we have pressure, we have kinematic viscosity. The unknowns are effectively here. These are the unknowns in the problem. And one of the issues with incompressible flow in general is that we don't have a prognostic equation to advance the pressure. That really makes it one of the challenges, computationally speaking, is to evolve the pressure field. So we have these four primary unknowns. And what I'm going to do is take these variables and the independent variables, x, y, z, and t, and effectively transform them into non-dimensional quantities. For example, u primed equals u over u ship. So what I've done here is I've taken the u velocity and I've normalized it by a characteristic velocity and created this variable u primed. If I choose this characteristic velocity to be a reasonable one, in this case the ship velocity, that is sort of the maximum velocity that we will see in the domain. If we consider a problem of a fixed ship with the water moving past it, the velocities may get a little faster than the ship because they're accelerating around the edges. At places they will be zero, such as where they stagnate on the front of the ship. So if I draw the flow field right here, we have u coming in. Let's draw from the stationary, where the ship is stationary and the water is flowing past it. It's going to create a wave train. So right on the bow, the velocity will be 0. Out here will be equal to u ship. And maybe on the edges of the ship where it accelerates around, you might see something like 20% higher than u ship. But this is a good characteristic velocity, which basically means these velocity fluctuations are order 1. U primed is order 1 because it gets to maybe 1.2. It ranges from about 0 to 1.2, or we might say negative 1.2 to 1.2. The ranges of u prime. So because we've picked u ship, if we normalize the velocity by, say, the speed of light, everything's going to be order 0. Or if we normalize the velocity by, say, 1 nanometer per second, then everything's going to be quite large. My goal is to make all the terms the same order. So if I do that with u ship, if I take a time scale, a good time scale for the problem is t times u ship over L. I can think of it this, where L is the length of the ship, or I can think of this as T over tau, where tau is equal to L over U ship. I'm just going to write subscript S, L ship over U ship. So that's sort of the time scale of passage of a flow parcel. If I have a ship again here, how long does it take this parcel to get from here to here? It's approximately this. We have to go the distance L. It's moving roughly u ship velocity. So if I normalize my t by this tau, my t prime, to create this variable t prime, this variable is also going to be order 1. So again, I repeat the same thing for all the different variables. Pressure, we know, ranges from stagnation to roughly the dynamic pressure here. So I have P over rho U squared ship. So I'm going to normalize that by the dynamic pressure. That's my P primed. For my independent variables, I did T already. Let me do X. Length scales in the problem, they range from 0 to roughly the ship scale. I won't see things in the problem that are much bigger than the ship scale. The ship generates waves, but the wavelengths are going to be smaller than the ship. So things are happening roughly at ship scale. We have X over LS, and the same with Y, etc. Go on and on. So then what I do is I take terms in the equations. Let me just take one, for example. If I have my acceleration term, this is the acceleration of the x direction velocity with respect to time. It's the acceleration velocity. It's the rate of change of the velocity with respect to time. This is a local acceleration. I can convert this into its equivalent non-dimensional form. So I take my two, let me just refresh here. I had U primed equals U over U ship, and therefore U I can write as U primed times U ship. I mean, U ship is a constant. And T I had written as equal to TU ship divided by L ship. So I can write T equals T prime times L ship over U ship. Okay, now I'm going to take these quantities here and I'm going to insert them into my partial U, partial T. So this is going to be equal to partial U primed US divided by partial T primed LS over US. So here again, these are my non-dimensional quantities right here. I solve for, I flip it around to solve for the dimensional quantities in terms of U primed and these constant characteristic values. And then I insert them in this just one term from the momentum equation. Now I can pull out my constants. So I'm going to put this US up top, pull this US out here, and pull LS over here. And I'll end up with US squared over LS times partial U primed, partial U prime, partial T primed. If I keep going through this process right here, with the advection term, with the pressure term, with the viscosity term, I'm going to end up with an equation that looks something like this. I'm going to maybe run out of space, but I'll try to. I'll have US squared over LS times partial U prime, partial T prime, plus US squared over LS. It works out to be the same constant out front here, times U prime, partial U prime, partial X prime. The other advection terms look the same as that, plus that, equals, now I'm on the right-hand side, let me continue this down here. The pressure term, scaling, ends up being the same, times partial P prime, partial X prime. And I have my viscosity term, which is going to be nu U ship over L squared ship. Now, this is the only term that looks different in the x momentum equation is this one. Everyone else is pre-multiplied by the same factor. The momentum, the advection terms, the acceleration term, pressure gradient term are all multiplied by the same factor. Now, if what I do is multiply through by the inverse of that factor, LS over US squared, I end up with an equation and take into account that each of these fluctuations, for example, partial U prime, partial X prime, is of order 1 because my U prime is of order 1, my X prime is of order 1. This term is of order 1, as are all the terms, because I specifically designed the non-dimensional quantities using the correct characteristic lengths. So they will all be order 1. So this is order 1, order 1, order 1, and I left out my actual derivative right here. Partial squared U prime partial X prime squared. Also order 1. Now I multiply through by ls over us squared, and I get, so this term right here just cancel out, become 1, 1, 1, and I have this term which is something special. So I have order 1 is now my acceleration plus order 1. All my vection terms, there's 3 there. Order 1, there's my pressure gradient term, plus over here I have equal to, I have 1, well, let me write it this way. I have nu over u ship L ship times order 1. Again, that was by multiplying L squared, LS over US squared times this term right here. That's what I end up with. If you look at this, these terms are all of the same size, order 1. This term has this thing out front. What is that thing? That's equal to 1 over the Reynolds number, US LS. So I have this equation. I took my momentum equation. When I non-dimensionalize it, out pops this special term. Order 1 plus 1 over the Reynolds number times another order 1. It tells me that if I look at these terms for the ship problem, that these are all of the same size. The acceleration, the advection, and pressure gradient are of equal importance. How important the viscosity is, the diffusion, I should say, term, depends on this particular parameter right here. It depends on this Reynolds number. For very high Reynolds number problem, high Reynolds number flow, it becomes less important. For lower Reynolds number flow, it becomes more important. So it tells me how important this term is. So we can see that this particular parameter, Reynolds number, which is a velocity characteristic length divided by the kinematic viscosity, comes from non-dimensionalizing the equation. This parameter pops out of there, a special parameter. And what is used for u, l, and nu depends on the problem and convention. For the ship problem, u is going to be the ship speed. L is going to be the length of the water line. And nu will be the kinematic viscosity. So for RE for the ship is going to be equal to U ship, I'll just write it as L ship here, but that is the water line length divided by the kinematic viscosity. One nice thing about the kinematic viscosity, or about working with waters, nu is approximately 1 e to the minus 6 meters squared per second in SI units. That's 1 over a million. So if you have your Reynolds number, well, let's say you have a ship. Let's say, just for an example, that that the velocity of the ship was equal to, say, 3 meters per second, and the length of the ship was 10 meters. Then my Reynolds number is going to be approximately equal to 3 times 10 divided by 1 e to the minus 6, which is equal to 30 million, 30e6. So for ships, your Reynolds number in millions is equal to this numerator. So basically, RE in million is approximately, because kinematic viscosity is not exactly equal to the value, RE in million is approximately equal to U times L. So if you know the velocity in meters per second and the length in meters, then you have already an estimate of RE in millions. Ship scales are typically million for a model, up to billions, million to billions for a large cargo ship or aircraft carrier will be in the billions. Million to billions is the kind of range that we're dealing with in this class. So that's a factor of 1,000. It's a pretty large range in Reynolds numbers. I won't go through the analysis, but we can do the same with the W momentum. If we take the W momentum equation, go through the same process, we will see there is one standout term in that equation, an additional standout term in that equation, I should say, which is the Froude number. Let me just write it as it would. If we went through the process with the W equation, we would end up with order one terms, the advection, the acceleration, pressure gradient, and we would get an additional term here, which is going to be order of Froude number squared, and I'll define that in a second. This is going to be the gravity term, the original gravitational term. When we non-dimensionalize that, the gravity term, the source term in the problem, turned into this. So it tells us as Froude number, which is equal to U over root GL. As Froude goes up, the gravitational effects become important, namely waves. Effects are important. So I'm going to write this as waves become important. It's vanishing Froude number. If Froude number goes to 0, we can neglect the influence of waves. As the Froude number gets larger, we can include the influence of waves. Now, Froude number is written this way. This is by convention. You could have easily defined the Froude number as, sorry about that. That was the storm alert. You could easily define the Froude number as U squared over GL. That would be fine. But by convention, it is U over root GL. This is related to a wave velocity, a wave celerity, a surface gravity wave celerity. And this is related to the ship speed, because if the Froude number of the ship, this is the ship speed, and this is the waterline length. So this square root of, so the units in the numerator and denominator are velocities. It's a comparison of two velocities, the ship velocity and a velocity of, this parameter at the bottom is not equal to, but it's related to the velocity of waves with the wavelength L. So it's a wave speed. It's a ship speed and a wave speed comparison, a ratio. And that is the Froude number. The Froude numbers we'll be looking in the class range from 0 to, maybe about 0.5, something like that. Actually, we can get a bit bigger. I take that back. We will probably see close to 1. So these are smaller range in that sense in class versus the Reynolds would be about 0 to 1. Now the key thing is that these numbers, the Reynolds number and the Froude number, they tell us something about the flow, whether viscosity is important, whether waves are important, and they come from non-dimensionalizing the equations, the governing equations. We also saw them arise when we did the dimensional analysis, when we took the ship's parameters. So we talked about having drag. We have drag, for example, and density and viscosity, and we had the ship speed, and we had the ship length, and we had gravity, and we put these together, and we found out that we can write this as a drag coefficient is equal to a function of the Reynolds number and the Froude number. So it's a relationship between 3 fundamental non-dimensional quantities. Now a drag coefficient by convention is normalized. It's a force, we'll call it D here as a force, divided by the dynamic pressure, 1/2 rho U squared. This 1/2 is a convention, so make sure you have it in there, times a characteristic area. And that characteristic area depends on the problem that you're interested in solving. For the ship, we will normalize by the resistance, or a resistance component, divided by 1/2 rho, or rho is the density of the water, U is the velocity of the ship, and S is the wetted area of the ship. It's the area, when the ship makes contact with the water, the area of the surface area that's wet is S wet, and that is units of meter squared. So again, we can relate these quantities. Dimensional analysis tells us we can relate these quantities, that there's some functional dependence between these. The idea of model testing is, the goal of model testing is to achieve dimensional similarity. If I can say that if I can set Reynolds number of my model equal to Reynolds number of full scale, let me call it RES, and at the same time set Froude number of the model equal Froude number of the ship, then that tells me that the drag coefficient of the model is equal to the drag coefficient of the ship. However, we determined this is not possible. We cannot maintain full dynamic similarity and have the Froude numbers match and the Reynolds number match. We can't do it without making up some new imaginary fluid. So what is done typically is a decomposition. We assume that we can take our drag, which I'll call our total drag coefficient, CT, and divide it into two pieces. One is a wave drag piece, and we'll say that's only, which in general, let me put it this way, which in general will be a function of Reynolds number and Froude number, plus a frictional drag coefficient, which in general is a function of Reynolds number and Froude. What we're going to do is make the assumption that the wave drag is only a function of Froude, and the friction drag is only a function of Reynolds number. Now that's not entirely correct. It's maybe a little bit easier to think about the effect of Reynolds number on, Froude number on friction drag. As the ship moves, the wetted area will change because the waves are evolving along the side of the boat. Some parts of the boat become exposed. Some parts of the boat are not exposed. Those waves create pressure gradients which influence the boundary layer. So this wave-making process does affect the boundary layer, but we're going to ignore that effect. Same with the wave drag. The presence of the boundary layer along the hull, which effectively is a viscosity effect, a Reynolds effect, will affect the wave making, but we are going to ignore that. And that greatly simplifies this problem because I'm writing this now as a wave drag coefficient as a function of Froude plus a frictional drag coefficient as a function of Reynolds number. Now, since we are maintaining that the Froude number of the model is equal to the Froude number of the full-scale ship, that means that the wave drag of the model is equal to the wave drag of the full-scale ship. And that is what's exciting about maintaining this. By doing this decomposition allows me to reinvoke dynamic similarity, even though I only have dynamic similarity in one variable. If I match the Froude, then my wave drag coefficients, this portion of the total drag, is going to be matched between the model and the full scale. What do I do about CF? So this we can learn from model testing what this is. Will get us here, which is good because waves are hard to estimate. Skin friction is not going to be correct because Reynolds number of full scale ship is going to be bigger, and in some cases much bigger than the model scale Reynolds number. So my skin friction coefficients are not going to match. So what I'm going to do is I'm going to use empirical data. And we'll be talking about this in our lecture on boundary layers. Empirical data, which will give me a mapping of CF as a function of the Reynolds number. So if I know the Reynolds number of my full-scale ship, that'll give me my drag coefficient on the full-scale ship. And now I have CF from that, and I have my CW up here. I can add them together, and I have my CT again. CT on the ship is CF on the ship plus CW, the wave drag coefficient on the ship. This is coming from model testing, directly from model testing. This is coming from our empirical studies or relationships, standard relationships between Reynolds number and drag coefficient. Drag being drag from skin friction or from boundary layers, stresses acting on the wall of the ship. So we're going to be tossing around these non-dimensional numbers quite a bit this semester. You'll have to be comfortable converting between them, but just note these two key parameters, Froude and Reynolds, and understand how these get tossed around. They're used in all different applications, not just ship flow. Froude numbers are used for all over oceanography In those cases, U is obviously not the U ship. L is obvious. L is commonly a depth instead of a length. So the parameters, the numbers in the parameters depend on the problem you're solving. So again, this is U ship divided by root GL of the water line. I'll put water line here. And Reynolds number is the velocity ship times the length of the water line divided by nu. And again, you can get a pretty easy estimate of number in millions just by multiplying the numerator together, because the nu is 1/1,000,000. So these are the parameters that we will be studying a lot this semester, and these drag coefficients are important to get to as well. So again, if you have, say, the total drag on the ship is going to be equal to the drag, this would be the total resistance of the ship divided by 1/2 rho times the ship velocity squared times the wetted area, I call it SW, of the ship. This is just how it's done by convention for the ship world. That is the static wetted area. It's the wetted area of the ship when it's at rest in the water. This is the ship speed of interest, and this is the density of interest. Note that in these problems, for example, the fundamental curve of Reynolds number, of friction versus Reynolds number, it does not have to be that Reynolds number. I'll just show approximately what this curve looks like. You have Reynolds, you have your skin friction here. There are different relations, but we'll see that they mostly look something like this in log space, where I have CF is decreasing with Reynolds number. So that's non-intuitive. The skin friction is decreasing with Reynolds number? No, it is not. For example, in Reynolds number, think about it here. Let's say we have a fixed, let's scratch that. Let's say we have a fixed ship of length L and a fixed kinematic viscosity, and we are changing U's, right? So that's going to, increasing U will increase the Reynolds number. It appears that skin friction is dropping with increasing Reynolds number, but it's not. This is skin friction coefficient. By the time you get converting back to drag, so if I say frictional drag, dF, is equal to CF, the frictional drag coefficient, times 1/2 rho U ship squared S wet. Note the US squared in here. So because I might be increasing Reynolds number by increasing the ship velocity, here I have a ship velocity squared in the numerator. So even though CF might be decreasing with Reynolds number, I have the drag going up. The drag will still go up because there's a quadratic dependence on the right-hand side here, even if everything else is constant. So I think for most of the relationships, we'll see that the non-dimensional quantities actually decrease with Reynolds and or Froude, but this because of in their ranges of interest, but because of this dependency, it means the dimensional drag is going in newtons is going to rise. All right, that's all. Just wanted to go through that.